What we were dealing with in the previous section was that of simple inequalities. Now we're going to move into compound inequalities. Now we're still going to restrict ourselves to one variable in these inequalities, just like we were with the simple inequalities last section. Ultimately, the distinction between a simple inequality and a compound inequality is that when it's a simple inequality, you just have one comparison between two quantities, so like 3 is less than or equal to 5.2. And then if you just have that comparison only, that makes it a simple inequality. Whereas if you have a compound inequality, you have to have multiple comparisons going on at the same time that we join together with certain conjunction words, like the word and or, and those are going to be the two conjunction words that are going to join up the compound inequalities that we're going to take a look at. So like if you had 1 is less than x, and 5 is greater than x. That would be an example of a compound inequality because you've got more than just one inequality going on in some sort of way to join and relate those inequalities together with one another. So it's really important that we understand the concept of compound inequalities, and that will help us to apply it to the actual algebraic and mathematical applications of compound inequalities. So you can see a statement right here that says, I am cold and it is snowing, really emphasizing that word that you see right there, which is the word and, that particular conjunction. It's really important that we understand what the word and means. So what I'm going to create right here is I'm going to create a table, and it's going to be a truth table. So what I'm going to put as a label for the first column there is C. That's going to stand for the cold aspect of the sentence. And then the second column, I'm going to put S for the snowing aspect. So I'm going to put true and false values here. So it could be the case that it is cold outside and snowing, so hence I put T and T for true and true. Now, it might be cold outside, but not actually snowing, right? You can think of actual real scenarios where it's cold and not snowing. This one's maybe a little strange to think about, like that it's not cold but snowing, but just go with it. And then there's also times, of course, where it's not cold and it's not snowing, right? So like in the summertime, obviously it's usually not cold and not snowing during the summer in the northern hemisphere. All right, so based on those truth values, we want to determine the truth value of this right here, the fact that it's cold and snowing. So think about this then. If it is true that it is cold and it is true that it is snowing, then is it true or false that it is cold and snowing? And the answer to that, it is true, right? And then if it's true that it's cold and it's true that it's snowing outside, then is it true that it is cold and snowing? And in that case, no, it's not true, right? And then in that case, it's false that it's cold, but it's true that it's snowing. So is it cold and snowing? And the answer is no, right? And then of course, in the case where it's not cold and it's not snowing, then it can't be cold and snowing, right? So then it's false. So the only time we got a true statement for an and statement is when both of the individual conditions were true. And what that means is that for I'll put it in quotations, an and statement to be true, so to join a bunch of things together with the word and, for an and statement, let's erase that comma, to be true, all of the conditions, the individual conditions that are joined together with and, need to be true, right? So you need all of those conditions to have that same truth value of trueness for that and statement to ultimately be true. So and means like both or all, right? So if we put this more in a mathematical perspective, you can see that we have this statement right here and that statement right there, and this word and. So you need to really think about this whole thing is really one statement. I mean, you got like individual sub-statements, but together it makes one statement because they're joined together with the word and. So in order to make this statement true, we need both conditions to be satisfied at the same time. So if you only had it where you only had this sub-statement, x is greater than or equal to -1, then that means you're dealing with that solution set, right? That solution set is going to make that first sub-statement true. And then if you were dealing with this right here, where x is less than 3, then that's going to be dealing with those values right there, right? But what I showed in the red and the blue colors right there is what's making the individual sub-statements true. And what really matters is to satisfy an AND statement, we need both of those things to be true at the same time. And the only numbers that are going to make both of those statements true at the same time are going to be those numbers in that interval right there. So what I'm going to do is I'm actually going to erase all of that because that helps you to see and understand what's going on. But really, we should only have the following sets of numbers between -1 and 3. So notice the dots that I made, right? We're going to include the -1 but exclude the 3. There's a more common way, though, that we express intervals like this, where you're looking at numbers between two different numbers. The most common way that we can do this is that if I call the numbers that I've indicated in the interval there x, then the more common way we'll write this is we'll say that the lower bound of -1, okay, since it's got a closed dot, it could equal to, but it's underneath the values that x are, because x is in that interval, but the numbers that x are can never get higher than 3, so we're going to say that it's less than 3. So pay close attention to those symbols that I used, right? So because that was a less than or equal to, we had that filled in circle right there, and then the less than right there, you can see, corresponds to the fact that we had an open circle right there. So this right here and this right here, they're the same exact statements of writing an AND. It's just that I think mathematically you'll kind of see it expressed as one kind of inequality statement right there, that compound inequality. All right, so now we want to take a look at just being able to solve various inequalities, and these are going to be compound inequalities, so compound inequalities of the type where we've got the word AND involved, which means that you need both conditions to be satisfied at the same time to ultimately make the whole statement true, right? So it says to solve each inequality and then graph the solution set. Basically, you just have AND joining two different inequalities. And in order to solve this, all you really need to do is just solve each of the individual inequalities. So it's no different than what we were doing in the previous section with simple inequalities. So if we go to the first one right there, you can see like, oh, well, we could divide by 3, but then you're like, I got to divide that by 3. So a maybe nicer, slicker way is to alternatively think, well, I can also multiply, because if I do 1/3 times 3, I get 1x, right? And then if I take this and I multiply it by 1/3, makes it a little easier, I guess, for us to be able to multiply right there, because then you just have -9 times 1, which is -9, and 2 times 3, which is 6. Now, as we're dealing with inequalities, let's remind ourselves that if you ever do multiply or divide both sides by a negative number, then of course you got to change the direction of the inequality. We don't have to do so here because we multiplied by 1/3, which is positive. So we just have x is greater than -9/6. That can be reduced, so we end up getting that right there. So then we'll want to deal with the other inequality and solve that one. So we'll have to undo the adding of 1/2, so I guess we'll have to subtract 1/2 from both sides. That means we're going to have to do a little bit of common denominator work on the left-hand side there. So if we have 19/6 and we're trying to subtract 1/2, we need a common denominator for the 6 and the 2 there, which would be 6. So we can leave the first fraction as it is. We'll want to multiply this one by 3/3, so we get the common denominator of 6 there. So that is then going to yield us 19/6 minus 3/6 is greater than 1/3 x. And then we can subtract those fractions now. So 19 minus 3 is going to give us 16/6 is greater than 1/3 x. I guess we can probably reduce that left-hand side, so that would be the same thing as 8/3. And then to undo the multiplying by 1/3 there, we can multiply by 3, and then similarly multiply that by 3, which we can treat as 3/1. So we're going to get 24 over 3 on that side is greater than 1x, because 1/3 times 3 is 1. 24 divided by 3 is 8, so we get 8 is greater than x. Okay, so a lot more work on that second inequality right there. So if we put this like all together, the solution for this is going to be that x needs to be greater than -3/2 and 8 needs to be greater than x, which I'll write that with x on the left-hand side. So if 8 has to be greater than x, then x has to be less than 8. And that's going to give you the solution set for that particular inequality. Now, whenever we're dealing with and inequalities, it's, like I said earlier, more common to kind of write this as one statement altogether. So we can say that if x has to be above -3/2, so you know if -3/2 is there, but then x has to be below 8, okay, we're dealing with these numbers right here, so we can write that by saying -3/2 is actually less than x, which is less than 8. So that's an equivalent way to write that out. And then I've graphed it on the number line. The only thing, though, is that because both symbols that we have are strict less thans, then we'd want open circles at both of those endpoints there, since -3/2 and 8 would not be solutions to that component inequality. All right, excellent. And then this guy right here is actually the same type of component equality as joined together with an and, because really you could think about it being like you have one individual inequality right there where you're comparing that side with this side, but then you also have another inequality where you compare this same side that we had with the other inequality with this number 5, but then it's just all joined together. Ultimately, it's really simple to solve these sorts of inequalities because really you can just think about the fact that you can just do the same thing to all of the sides, but there's kind of, I don't know, 3 sides if I want to call it that. So we're just trying to solve for, I guess, y, right? So I guess there's some cleanup we could maybe do with what's going on right there. So if you distribute, you get 10y, and then 2 times 3 is plus 6, but we're going to have to subtract 1. So you really have 10y plus 5 in the middle right there, and then it's still less than or equal to 5, and then you have the -45 that's less than or equal to that. And then you just do the same thing to all of the sides to get the y alone. So like you want to subtract the 5, right, to get just 10y alone. Just do the same thing to all of the parts right there. So then you're going to end up getting -50 less than or equal to 10y less than or equal to 0. Note that because we subtracted there, that we don't have to flip the inequality symbols, and then we're just going to divide by 10, which when you divide by a positive, you don't have to flip any inequality symbols there either. So that's going to give you -50 divided by 10 is -5 is less than or equal to 10 divided by 10 is 1y, and 0 divided by 10 is 0. So we end up getting this as your solution set for y. And then to graph that, of course, then you would just have -5 there, 0 there. Both of the symbols are less than or equal to, which means those numbers are going to be included in your solution set, and then all the numbers in between also are possible values for y. So that gives us a graph of that solution set for that inequality. Cool. Okay, similar sort of thing right here. Just an interesting thing is going to happen. So if we're going to solve for r, we're going to want to subtract 5 from all of these different parts right here. It's going to give you -13 is less than -r is less than 2. We didn't have to flip any inequalities because we didn't divide by a negative, but then if we want to get a positive r alone, we could divide by -1, which then means here, because you're dividing by a negative, then you're going to have to flip the inequality symbols, which means you're going to get negative divided by negative is a positive, flip the inequality symbol, that's going to become positive r, and 2 divided by -1 is -2. So we end up getting this, solution set right here. Now, here's the thing, is that there's a lot of ways that we could kind of write stuff out. So like, okay, so if I write 1, 2, and 3, I'm just making up an example here to demonstrate how you're supposed to write this out correctly. So of these combinations of ways we can write stuff. So with this right, let me get the right thing to write with here. Okay, so with this right here, it says that 1 is less than 2, which is less than 3. Okay, that makes sense. Okay. Also, maybe should have written this third one differently. So this makes sense. Also, 3 is greater than 2, and 2 is greater than 1, right? So these two make sense. With the other ones, though, so this guy right here and this guy right here, they don't really make sense because those signs are kind of like pointed outwards, right? And then these signs are pointed inwards, and if you can like compare stuff there, it doesn't really make sense. So you don't ever want to have those inequality symbols pointing different ways. So like either both are pointing to the left or both are pointing to the right. But it just turns out, though, that we like to have the smallest number at the left and then the largest number at the right. So even though this makes sense that you have 13 is bigger than r is bigger than -2, you don't want to leave it like that. You should always have the smallest possible number at the left-hand side. So you're going to want to rewrite this as being -2 is less than r is less than 13, and that's the preferred way of writing that. So you should always write it like that. So similarly, you should always write it like that versus like that. You don't want to do that. Even though, like I said, that makes sense. Most often you want to have the smallest number at the left-hand side. And then, to graph this, you got -2 and then 13. You're going to have open circles for both of the endpoints since it's just strict less thans. Excellent. Okay, and then this one's kind of getting us back to just two separate simple inequalities, but it's not a simple inequality because it's joined together with the word and, so therefore we got this whole thing to be a compound inequality. Just got to solve each of these separately. So I'll just kind of do that pretty quickly right here. Okay, you got to divide by a negative now. So because you divide by a negative, the inequality symbol now switches, it becomes a less than or equal to. So we get that. I'll rewrite that as z has to be greater than or equal to 5. And then we'll solve the other one. Okay, you're dividing by a positive, so you don't have to change the direction of the inequality. So you get that. So ultimately, we're going to have it that z is greater than or equal to 5, or that z is greater than -3. So I'm going to have to put some colors on this. So let's color that in red. So if 5 is right there, then we need it to be equal to or greater than. And then let's pick, how about like a green for that one right there. So z has to be greater than -3. Now -3 is a number that is, of course, smaller than -5, so we'll put it there. Now it has to be, I guess, an open circle at where -3 is, and then be greater than. Now I made a mistake. We're going to talk about ors in the next part of stuff. It should actually be an and because we have the word and. Now, and in order for an and statement to be true means that you need both of these things to be true at the same time. So I need both the red statement and the green statement to be true at the same time. So if you look at this graph right here, the only place you're going to get the red statement and the green statement to be true at the same time is where they're intersecting with one another, which will not be there at all because you're not going to get the red statement to be true there at all. So the only place where you're really going to get this statement to be true is just in the, I guess, red area, and that's where some of the green area was as well. So it turns out, right, because these were kind of both pointing towards the same way, you can actually simplify this statement to say that you're only going to get the red and the green true, really, when z is just greater than or equal to 5. So it's just kind of an interesting solution to that compound inequality right there. All right, and then one last final one right here. So it's, again, got two separate simple inequalities. So I'm going to go ahead and subtract 2t from both sides of this one. It's going to get me that, and then I'll add 17. So I get that, which I'll rewrite as that. Excellent. And then the other one, just got to add 13 to both sides, and it's going to give me that. So ultimately, we come up with that t is greater than 2, and since we got the word and that t needs to be less than -6. So if I graph this red one right here, here's 2, we need to be open circle and greater than. And then this green one right here, -6 is a smaller number, also is going to be an open circle. So now these are pointing in different directions, and because of this word and, it's meaning that I need both the red and the green to be true at the same time, and there's no way you're ever going to get this to be true at the same time. There is no number that's going to be greater than 2, and that same number is also going to be smaller than -6. So therefore, the graph of what this solution set should look like is it should look like that. Nothing, right? You aren't going to graph anything. And so, like, what we're saying also right here in words is equivalent to, like, it's the same as that, the empty set, right? Like, there's just absolutely no solution here.